Today's lecture is on section 3.1, exponential functions and their graphs. And as you all know, we're stuck at home because of the COVID-19. And so this website here, elpasocovid19tracker.com, shows the number of cases per day in El Paso. So for example, starting on March 13th, we had 1 case. Yesterday, we were up to 115 cases. And so if we look at the way this is growing, this is going to lead us into a conversation on what an exponential function is and what it looks like. So for example, if I was to draw a line here on this graph, it might look something like this, and this is going to keep going up. And so today this section will cover exponential functions. Then we'll be able to come up with a equation that can model this data. Okay, so before we start, just some exponential rules that we want to keep in mind. And so I have listed them up here. And so the product rule, whenever you have 2 exponents with the same base, then we're just adding the exponents. Here we're dividing, we subtract the exponents. If we have raised to an exponent, we multiply the 2 exponents. And make sure we review all of these. Another one to look at is a 0 exponent. Anything to the 0 power is always 1. And the negative exponent, if we have x raised to a negative power, we can write it as 1 divided by x to the n. So an exponential function, f with base a, is denoted by f of x equals a to the x, where a is greater than 0 and a does not equal 1. X is any real number. So in the past, we've been used to seeing things that look like this, and that was quadratic. These exponential functions kind of reverse the role of the location of the number and the variable. So this is exponential. Notice that your variable is now an exponent. So to evaluate these, if we have f of 1, then replace our x with 1. 16 to the first power is 16. So that would be our answer. The next one, f to the half power, 16 to the half power. If you want to use a calculator, that's fine. Just make sure that when you enter this on your calculator, you have parentheses around the half, or else it's going to give you an incorrect answer, depending on your calculator. But here, anytime you have a fraction as an exponent, this is going to become some type of root. In this case, the denominator 2 tells us that this is going to be the square root of 16. So the square root of 16 is going to be 4. Letter C. (16 raised to the 3/2). Again, since we have a fraction, the denominator tells me that this is also a square root. But then with the 3 in the numerator, it becomes the square root of 16 raised to the 3rd power. So 4 cubed is 4 times 4 times 4. So that's going to come out to 64. So again, the denominator tells you what type of root you have. The numerator tells you that it's being raised to that power. Here, x is negative 1. So we can use the rule for exponents on number 7. We can rewrite it as 1 over 16. And last, f of 0, anything to the 0 power is going to be a 1. So these are just examples of evaluating the function. Example number 2, the exponential function f of x equals 42.2 times 1.56 raised to the power of x. Models the average amount spent f of x in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at the shopping mall? So here x represents the hours. And so they tell us what is going to be the amount spent after 3 hours. So x is going to be 3. So when we evaluate this or simplify, you first want to do the exponential part. So we would use our calculator here, 1.56 raised to the third power. If you're doing it, entering it correctly, you should get 3.796416. I like to keep all the decimals until the very end. And we multiply our result times 42.2, and that comes out to 160.21. So after 3 hours, the average amount spent is, it says to round to the nearest dollar, so this would become $160. Okay, let's go on to page 76. So here, like any new function, we want to know what it looks like. And so I have filled in some of these tables already. But if we look at the first table for f of x, we have if f of x is equal to 2x, if I plug in the negative 2 here, then we get 1 over 2 squared, which is 1/4. And if you notice, I already have the 1/4 there. F of negative 1 would be 2 to the negative 1, which is going to be a half. F of 0 is going to be 2 to the 0, which becomes a 1. And f of 1 is 2 to the first power, which is going to be 2. And f of 2 is going to become 4. So if we do this same thing to each of these tables, then we have the following tables. So this is your f of x function, g of x, h of x, and rx. So again, these numbers on the y-axis here, or the y-coordinates, I got from doing the same process as I did here. Okay, so we want to graph these and compare the graphs. And also, we want to compare these especially. Okay, so let me graph the first one. Negative 2 and a fourth, so maybe around right here. Negative 1 and a half. 0, 1, 1, 2, and 2, 4. So my graph would look something like this. And right here, the x-axis serves as a horizontal asymptote. The next one, negative 2 and 4, negative 1 and 2, 0, 1, 1 and a half, and 1 and 1/4. So this graph will look something like this. Okay, so you notice how they're reflective on the y-axis. And if you notice here, we have 2 to the x, and this was 2 to the negative x. So this negative tells me that I'm going to have reflection on the y-axis. Let's try letter h of x. So I'm looking at this graph now. -2 and 4, -1 and 2, 0 and 1, 1.5, and 2 and a fourth. Notice that the points here are exactly the same as the previous function. And so in reality, these two functions are the same. Okay. And why are they the same? Well, we can look at the following. G of x is equal to 2 to the negative x. H of x is equal to a half to the x. So what happens here is I can rewrite this as 2 to the negative 1 raised to the x power, which will become 2 to the negative x. So this equation is the same as this equation. Okay, so now the last one, Rx. So we have 2 and 0.5, 1 and 0.25, 0 and 0.125. So again, we have 2 and 0.5, 1 and 0.25, 0 and 0.0125, so it's just getting smaller and smaller here, and -1. So these are going to get really close to 0. And so perhaps we need another number here. So here we would get 2 to the 3 minus 3, which is 2 to the 0, which is 1. So at x equals 3, we get 1. So this is going to start to move up this way. So as you can see here, by having the -3, we have a shift, and we move 3 units to the right. And so you can see from the graph, our original 2 to the x was the blue one. And now with the last function, the graph got shifted 3 units to the right. So if we look at all these graphs, what is the domain and the range for the above graphs? So as you can see, they all have the same domain of -infinity to +infinity because we're using all the x values. And the range is going to go from 0 to infinity. Notice I didn't use a bracket because the 0 is not included, as these graphs are approaching the horizontal asymptote. The y-intercept for the first 3 was, so first 3 graphs was at 0, 1. And the last graph, the y-intercept was at 0.0125, which is this point here. And the difference between these graphs, if we're looking at graph A, is an increasing function. It's the blue one here that's increasing. But graph B and C, which is the red one, is decreasing. And then the last graph, it has a shift 3 units to the right. So let's go on to the next page. So in general, we want to look at what these graphs will look like. So in exponential functions, we have what we call a growth function and a decay function. We're going to have a growth function if the exponent for x is positive and b is greater than 1. We're going to have a decay function if the x is negative and the b is greater than 1, or if the x is positive with our b between 0 and 1, in other words, a fraction. Okay, either way, the general form here, the y-intercept is going to be given by a. The domain is going to go from negative infinity to positive infinity. The range will go from 0 to infinity. It does have an asymptote at y equals 0, which is our x-axis. And the function is 1 to 1. What it means by 1 to 1 is if you have the graph, let me just draw the graph. This is the graph shape here. This is A. So in general, this graph is going to be increasing. 1 to 1 just means that the graph, if we draw a horizontal line, it's only going to touch at one place. And then for the decay function, the y-intercept is still at 0a. We still have the same domain and range, the same asymptote. It's still 1 to 1. The only difference now is that the graph is going to be decreasing. So the graph is going to come this way. So for the next example, example 4, let's look at the graphs on decimals.com to save us a little bit of time. And we can then compare them. So the first graph is 3 to the x. And then the second graph is 3 to the power of x. And notice if we add a 1, then the graph shifts to the right one. I'm sorry, to the left one. So our original is the one in purple, and then after we added the 1, then our graph shifted to the left. Or the third one is 3 to the x. And now we're going to be subtracting 2. But notice that the subtracting the 2 is not in the exponent. And so that causes the graph to move down. The next one has a negative in front of the 3. And so that's going to cause our function to have reflection on the x-axis. So notice it opened down. Okay, so that's the blue one. And so let me just take away some of these. And the last one is 3. But this time, the negative is an exponent in front of the x. And so notice that it gives you a reflection on the y-axis. That's the green one here. And so if we look at the next example, a to the x, and then we have a 8 to the negative x minus 4, describe the transformation. Okay, so we have some shifts here. And so let's take a look in decimals so we can see those shifts. Okay, so as I do this, think about what shift is actually happening. So first, I'm not going to include the negative in front of the x so we can see what would happen without it. Okay, so if I put a minus 4, notice that the shift is going to be 4 units to the right. But since it has a negative, that means we're going to have reflection on the y-axis. And so now you can see that your graph, the first one without the negative, just shifted to the right 4 units. But with the negative, this graph reflected on the y-axis, and so now we're on this side. Okay, so this is some examples of what the exponential function looks like. And so for the next part, I will make a separate video to talk about writing the equations of these exponential functions given some data.